Hello, so in this video I'm going to go through solving inequalities, simple and compound. So I'll go through first what a simple inequality is, a couple examples of those, some examples where you'll be given a graph of an inequality and have to write the equation or inequality for it, a couple more of compound inequalities, and then just one word problem, and that'll be it. Pretty short and sweet. So the first ones, we're going to solve these very similar to how you would solve an equation. The only difference is now we've got a greater than, a less than, a greater than or equal to, or a less than or equal to sign instead of the equal sign. So solve them the same way. What I want to do is isolate the x value. I can do that by adding 8 to both sides here. So if I add 8 to the left, add 8 to the right, I'm going to get negative 4 plus 8, which is positive 4, and then divide both sides by 4. And I'm going to get that x is greater than or equal to 1. So what this really means is if I take a value of 1 and I substitute it back in, I'm going to get negative 4, which is greater than or equal to negative 4. So that's a true statement. If I take any value that is larger than 1, such as 2 or 3 or 4 or 10, and sub it back in for x, it is also going to make a true statement because those would give me values then that would be greater than negative 4. So what we do is we make a small little number line down here. I like to just indicate a few numbers on here just in the event that sometimes we'll have fractions, and that if I suppose had an answer that was 1/2, I could put my dot right between 0 and 1. But what we're going to do is go over to where 1 is. We're going to fill in this closed fill in this dot and make it a closed dot because this says greater than or equal to 1. And then I'm going to draw an arrow to the right indicating that any value greater than or equal to that value of 1 makes that a true statement. In the second one, we need to use a distributive property first. So that's going to give me 2x minus 8 is greater than 4x plus 6. And then what I want to do again is get the x by itself, or get my x's by themselves. So I'm going to bring, oh my gosh, why did I just bring that 2x over? I'm going to bring this 4x to the left side by subtracting. And I have 2x minus 4x, which is negative 2x. I'm going to bring down the rest of my problem. And now I want to get this x by itself, so I can add the 8 to both sides. And that is going to give me negative 2x is greater than 6 plus 8, which is 14. And then what I want to do is divide both sides by negative 2. Now this is something you've probably seen before. When you divide by a negative coefficient to x, when we say a coefficient, we're talking about a number in front of the variable, so not the 14, but since the 2 is negative, I'm going to have to flip my inequality in order to make this a true statement. And 14 divided by negative 2 is negative 7. So when I put my numbers on my number line, I've got negative 8, negative 7, and negative 6. I just have a less than sign, so it's not less than or equal to, just less than. So open dot over the 7, and then drawing an arrow left indicating all those values that are less than negative 7. What we could have also done to solve this problem was actually from this point right here, and this is what I was doing originally before I stopped myself, is if I subtract 2x on both sides, I would have negative 8 is greater than 2x plus 6. And then I would bring the 6 over to the left side. Negative 8 minus 6 is negative 14. And I would have negative 14 is greater than 2x. Now the only difference is now my variable is on the right-hand side. When I divide here, I'm not going to flip the sign since the 2 was not the negative this time. So you get negative 7 is greater than x. So we think about numbers that negative 7 is greater than, and another way that I can rewrite that statement is to flip it then and say x is less than negative 7. And notice that is the same answer that we had before. So anytime you want to flip around, that's a property of symmetry, flipping your x and whatever number is on the other side of that inequality, you just have to flip the sign. Another distributive property, this one's got variables on both sides. So I'm going to end up with 3x minus 3 plus 2x is greater than 5 plus x. And what I want to do is gather these like terms here. So I've got a 3x plus a 2x, so that's 5x minus 3 is greater than 5 plus x. And just like before now, we want to bring all of our x's onto one side and all of my constant terms onto the other side. And I'm going to do that by adding 3 here. So I'm going to end up with, oops, this was a 5. Jumping ahead a little bit. So I get 4x is greater than 8, and then dividing both sides by 4, I get an x value that is greater than 2. Again, making a little number line just to indicate our solutions. we are talking about everything greater than 2. So an open dot and the arrow drawn to the right indicating the numbers that are larger than 2. And then for part D, again, bringing over all of our x's onto one side. I think this one's just going to have some fractions. So 21x minus 3x is 18x. Bring down the plus 7, bring down the inequality. I'm going to now subtract 7 on both sides and get 18x is less than or equal to 9. So when you divide both sides now by 18 to get the x by itself, you get an x value that's less than or equal to 9 over 18, which is also 1/2. So if you make a number line, sometimes what I'll do is just indicate that this would be our halfway point then between 0 and 1. Open dot, closed dot, because it says less than or equal to, and then everything that is less than that value of 1/2. So those are just basic, simple inequalities. So we did a couple of distributive property and variables on both sides. Now we're going to go into compound inequalities, and we'll start those by just identifying what's on the graph here. And you'll see some of the language that indicates then which types of solutions that we'll have. So in this first example, if I pick any number that's on this in this shaded area here, or this area that's drawn in red, you'll notice that this value of -2 is greater than this side, and it's also less than this side. So if I write this as an inequality, I can say that any value that I pick in here, and I can just put a random x right here, this x value is a value that is greater than -10, and that x value is less than 8. And notice how I said greater than and I just said less than, and that's because these are both open dots as opposed to this one down here, which will be a closed dot. So another way that you can write this, and this is a compound inequality where, again, your arrows point inwards here. So these two arrows would essentially be pointing in towards a value, and that value is x. It satisfies both. So another way that you could write this compound inequality is to say -10 is less than x is less than 8. And where that notation comes from, because it's like, okay, how did I just break this from 2 into 1? This right-hand side comes straight down, and then the other one would use that symmetric property that we did before, where this says x is greater than -10. If I flipped it, it would say -10 is less than x. And you'll notice that's where this part of it comes from, and then the x just remains in the middle. So again, it's another way, two things that express the same relationship. In this case, now you'll notice two differences, one of them being that the arrows point in opposite directions, and then the other being looking at our dots. One has the open dot, one has a closed dot. So it's something like this. You would just say x, and then we're talking about all the values that are less than 0. So x is less than 0. And on this side, we're talking about the numbers that are greater than or equal to 7. So the difference now is if you pick one value here, it's only going to make one of these statements true. You can't be a number that's less than 0 and greater than or equal to 7, indicating that the word that should be in the middle would be or. So you can either have a number that is less than 0 or greater than 7 in order to satisfy that compound inequality. Last one then, kind of a mix of those first two examples. So this one's got a closed dot on one end, and we also notice that we have an and inequality. So the arrow's pointing inwards. So you can either say x is greater than or equal to -6 and x is less than 0. Or we could also write this as that compound -6 is less than or equal to x is less than 0. And again, that's what we could use when we have those and inequalities. So solving compound inequalities just means we're going to be solving essentially a couple inequalities at one time. And what's nice is if I cover up this side, I would add 3, and that would get my x by itself. If I were to cover up this side, I would also be adding 3, and that would get x by itself. And the same thing in like this next example. If I were to cover this up and solve for x, you would subtract 2 and then divide by 4. And if I covered this part of it up, I would still subtract 2 and divide by 4. So what's nice is when we have these compound inequalities, I can just solve them all at one time. So I'm going to do this to isolate the x. I'm going to add 3. That's going to make it go away in the middle. 2 plus 3 is 5. I get 5 is less than or equal to x, which is less than or equal to 9. And what this is really saying is that x is some value between and including 5 and 9. So here would be 5, here would be 9. I know that 7 would be in the middle, here would be 6, here would be 8. So what I would do first is draw in your dots. And then we look at the fact that this part says x is less than or equal to 9, indicating everything to the left. This other side could really be written, if I write the x before the 5, you just have to flip this inequality. So that would be talking about all the numbers that are greater than or equal to 5. And again, that indicates one of those compound inequalities. That would be an AND inequality. The second one, like I said before, we can just solve this by subtracting 2 from everything first. Negative 4 minus 2 is negative 6. Bring down the less than, bring down the 4x, bring down the negative 2, and then I'm going to divide everything by 4 here. And this one's going to have fractions, which is okay. This ends up being negative 3 over 2, which is about negative 1.5. And less than x, less than, and negative 2 over 4 is just negative half. So this would be negative 1.5. This value would be negative 0.5. What I'm going to do is make a number line that looks something like this, and then just pinpointing where those two values fall on that number line. So negative 3/2 is going to be right here, and then negative 1/2 is going to fall right here, and these are both open dots. And then same as before, we're talking about the area that is between the two values for that compound inequality. So next we're going to take a look at compound inequalities with OR, and you'll see right in the actual directions that word OR is in there, indicating that, hey, we have to solve each of these separately. So in this first one, I'm going to add 4 to both sides and get x is less than or equal to, and negative 6 plus 4 is negative 2, or x can be a value, and if I subtract 2 on both sides, value greater than 3. So what I'm going to do is put these two values on a number line, negative 2, there's negative 1, 0, 1, 2, and 3. And we have a closed dot for this one on the left, and this one where it's 3 is an open dot. And you'll notice x greater than 3 would mean the arrow is going to the right. X less than or equal to negative 2 is everything to the left. So again, if you pick a value to make this a true statement, it can either be a value that is less than or equal to negative 2 or a value that is greater than 3. Same kind of solving for the next one. We'll keep going. I'm going to subtract 2 from both sides first and get 3x is less than negative 15. Divide both sides by 3, and I'll get an x value that's less than negative 5. For this second one, I'm going to subtract 4 on both sides and get 2x is greater than 3. And another fraction here, we got 3/2, which just like before is 1.5. So when we go to a number line, I've got negative 5 here, negative 4, negative 3, negative 2, negative 1. Here would be 0, 1, 2, and then if I wanted to keep going. But again, positive 3/2 is going to be at 1.5. So we can just mark off where that would be. It should be right here. This is where 3/2 would go. So we're talking about an open dot to the right of there and an open dot drawn to the left for that inequality. All right, next one, another compound here. So same way, subtract 1 from everything first. So this is one where, notice this expression is written right in the middle, meaning we can solve this all at one time. Negative 8 minus 1 is negative 9. Bring down the rest of the problem. 10 minus 1 is positive 9. So when I divide all these things by 3, I'm going to have the negative on the left side, and that's negative 3. I'm going to have just an x in the middle, and then I'm going to end up with a positive 3 on the right side. So here's my negative 3. 0 would be right smack dab in the middle. Here would be my positive 3. We can kind of dash this off to make a number line then. And we are talking about closed dots on both of these, since those inequalities say less than or equal to. And then we're going to connect the dots. So everything to the left of one, and then that symmetric property for everything that's greater than the other. And then this last one for f is just a little unique because the coefficient to x is negative on the inside. So what I'm going to do first is add 17 to both sides of this. And I'm going to obtain 5x plus 10 is less than or equal to negative 4x, and then that's less than or equal to, now this was 9 minus 2, which is 7, and if I add 17 to that, I'm going to get 24. And then I'm going to break this actually up into two inequalities from here. So this one on the left, I'm going to rewrite this over here. 5x plus 10 is less than or equal to negative 4x. And then this one that's on the right, I'm going to end up, oh my gosh, that shouldn't have been a plus 10. I am realizing this is a mistake and I'm too lazy to edit this video. I'm going to go back. That should have been 5x plus 27. Makes a lot more sense. I would have had like really ugly numbers, which is okay, but not in this video. So rewrite this as 5x plus 27 is less than or equal to 4x. And then this one on the other side, negative 4x is less than or equal to, and that was positive 24. So then in order to solve each of these, this first one, I'm going to bring the 5x to the right-hand side. So I get 27 is less than or equal to negative 4x minus 5x, which is negative 9x. And then this one, I'm going to divide both sides by negative 4, and I'm going to get x is greater than or equal to, so I had to flip that inequality. 24 divided by 4 is negative 6. And then solving this one, I'm going to divide both sides by negative 9. 27 divided by negative 9 is negative 3. I still have to flip this inequality to get that equal to or greater than or equal to x. And then last thing I'm going to do with this is apply that symmetric property, which again says I can flip this if I want to write x on the left side. So my solution then is I'm talking about all the values that are less than or equal to negative 3, but all those values that are greater than or equal to negative 6, which we could rewrite as a compound inequality. So something that would look like this. Essentially, negative 6 would be here. There's negative 5, negative 4, and negative 3. These were both less than or equal to's originally, meaning we are going to have closed dots on both, and then looking at the area that is between those two. So that was just a lot of practice problems with those types. Last one then, just dealing with a word problem and how you could see inequalities. And you hear it a lot when people say something is at least or at most. Or greater than, or they'll say less than. So suppose a tutor charges an hourly rate of $30 per hour and an initial fee. So our variable in this case is going to be the number of hours. How many hours must they work to earn at least? So there's our at least $500. And we want to write and solve an inequality. So we're going to let x represent the number of hours that this person is working. And then we know that it's $30 for every one of those hours. Plus they charge a fee of $40. So if they work 2 hours, we would just substitute 2 in for x. That would be 60 plus the 40 would give me $100. But we want this number to be at least, so greater than or equal to 500. Sometimes when people hear the at least, you want to put the less than sign, but think about numbers that are at least 500, like 600, 700, 800. Those are all numbers that are larger than 500, which is why the greater than or equal to shows up. And then solving this, pretty short and sweet. I'm going to subtract 40 on both sides, get 30x is greater than or equal to 460, and then we're just going to divide both sides by 30. And this is where it says that we want to write and solve this inequality to the nearest hour. When I divide both sides by 30, I get x is greater than or equal to 15.3 hours. So if this person works 15 hours and essentially a third of an hour, so 20 minutes, they would meet that. But we want to round to the nearest hour. Now, if this person works 15 hours, if I sub 15 in for x, I would get 450 plus that initial fee of $40, and that would give this person $490, and that is not at least 500. So this person would need to work at least, and then you have to round this up, 16 hours. So the tutor would have to work at least 16 hours to earn $500. All right, so quick review of all the stuff that we went through, starting with the problems that were just simple inequalities, graphing on a number line. We did some more practice with that and what happened when we divided by a negative and flipped the inequality. We started our introduction for compound inequalities by just writing them based off of the graphs, and then we solved compound inequalities using some of the ands and some of the ors, and we got some of those tough ones in there as well, and then we ended up with a word problem, and that is it.